So as an organizer, there's been a lot going on my mind. So if I come across incoherent, please apologies for that. Straight off the bat, I want to address a thing that has been discussed just now, that, you know, like how much do you show the feminist side of you? And I have completely always shown the feminist side of me in ICTS without any apologies. And the nice thing, of course, I have to admit, is that ICTS is one of the more progressive places. So it hasn't, I haven't gotten that much flack, I think. I might not know what flack I have gotten. And also what happens sometimes when you do that is that some people who actually have similar ideas do find you like a safe person to talk to. And it is not just women, and also the men in the faculty who have some ideas. They actually want to bounce it off you and find a resonance with you. And so this helps them to also, like, you know, make the conversation. So yeah, so let me get into this talk. The kind of problems I've been working on broadly are on astrophysical fluid dynamics and plasma astrophysics. The usual pitch is that, you know, most of the visible universe is basically in plasma state. So we need to study the plasma nature of this side of the universe. And so some of the fundamental processes that I study are dynamos, turbulence, magnetic reconnection, and so on. So dynamos are required to understand the existence of large scale and small scale fields that we see in many astrophysical systems. And one of the main agents that is driving this dynamo is turbulence. And turbulence is basically ubiquitous. It's there in sun, stars, galaxies, galaxy clusters, accretion disks, and so on. And one of the very interesting many energetic events that occur in many of these systems can be modeled on basis of reconnection. So I'll talk about it more a bit later. So these are some of the kind of direct astrophysical applications of these, besides you know, explaining cosmic magnetism. So I'll be touching upon the first and the last one, and not the second one so much. So that one is basically about, you know, dynamos in galaxy clusters, bringing up reconnection sites, and these sites then become places where, you know, you can have reacceleration of cosmic rays, which was talked about by Ruta earlier today, and that can go to explain non-thermal emission and so on. Yeah, so let me get into the first problem. Yeah. So recently, not so recently, in 2010, gamma ray astronomy has put some constraints on magnetic fields in cosmic voids. So basically, the story is like this, that you have these TeV photons from blazars, and then they interact with extragalactic background light to give you electron-positron pairs. And these then upscatter the CMB photons to give you GeV photons. And this is the idea, that you should see GeV photons, but you don't. And then the explanation is that you have these large-scale magnetic fields, and you can put constraints on these magnetic fields. And the constraint is that you can get a lower limit of 10 to the minus 16 Gauss, or on megaparsec scales. So the plasma in cosmic voids is extremely thin, so it's difficult to have dynamos over there. And thus, it is thought that these magnetic fields must be coming from early universe, or it is of a primordial origin. And yeah, so if we go back to early universe and ask what's happening over there, so you have this decaying magnetohydrodynamic turbulence that operates in the early universe. And so this is work that was done in 2021, where we looked at the system in many different simulations. And so one of the main results of this work is that we showed that this kind of system is being driven by magnetic reconnection. And so what you see here in these plots is that the the magnetic field decays over time as a power law, as a power law function. And what you see are these curves from these different simulations with different Reynolds numbers. And here are simulations from 2D systems, and this is from 3D simulations. And what happens is, if you take into account that there is reconnection going on in this system and then normalize the time by reconnection time scale, then all of these curves collapse on top of each other, giving you an empirical evidence that reconnection is ongoing in these systems. So let me briefly now tell you what is this magnetic reconnection. So this is basically a process in which oppositely directed field lines come towards each other, and at the interface there is a current sheet, and right at the current sheet they break and reconnect, and the reconnected field lines then exit the site of reconnection due to magnetic tension in the field lines. So this basically involves topological rearrangement of magnetic fields, and there's a conversion of magnetic energy to kinetic energy. So you can see that this process inherently is going to decay the magnetic fields. So in the 2021 paper, we also proposed that this this can be explained by one more constraint in the system. So the way we go about modeling the system is to say that there is a power law decay, and this is a simple equation that kind of describes that. This was already like a phenomenological model proposed by Kolmogorov long ago for hydrodynamic decay. And so we kind of recycled it for this problem. And now what you need is, to solve this equation, you need two ingredients. One is the time scale tau over here, and then you need to have some overall conserved quantity in the system. Okay, so the time scale, we have already said that magnetic reconnection is important, so it's the magnetic reconnection time scale. The conserved quantity, we propose that it is vector potential squared. Now, this vector potential squared is also known as anisotropy. Maybe a strange quantity to like a lot of you, but this is connected to the idea that there is magnetic flux freezing, which is a ubiquitous manifestation of magnetic fields, that magnetic fields are flux frozen, especially when the conductivity is very high. And so this leads to the correct power laws, in the sense that the simulations basically reproduce the power law that we answer that we get by plugging in these things. And so then you may ask, okay, this is like a 2D conserved quantity. What does it have to do in 3D systems? And I've been telling you that reconnection takes place in 3D systems. And also, I want to point out that, the interesting thing about the reconnection is that it allows for these magnetic structures to merge and form larger and larger structures. That is what you see as the system evolves. Okay, and so the other thing that we understood is that because the system has these magnetic fields, it's kind of anisotropizing it, so it's making it quasi two-dimensional. This is something that was looked at by Shreya and Chandranathan. Chandru is right here in the audience. Sorry for pointing at you. And so now he's also looking at the spectral evolution aspect of this. Okay. Yeah, I think I need to go faster. So basically, I just want to say that this study has allowed us to now be able to explain those cosmic void fields. So this particular plot tells us that if you follow the evolution that is proposed by us, then it basically allows you to be above the stuff that is taken off by the observations. Okay, so now next I want to come to this context. So this is about jets around black holes, and this has been already introduced to you by Preeti, so I'm not going to say anything more about this. Okay, and I will directly start talking about this. So the idea is that you need to have magnetic fields to support these jets. And where do these fields come from? right? And so usually around these black holes, you have these disks. And in the disk, there is plasma, and plasma can give rise to dynamo. And dynamo is basically a process which converts kinetic energy to magnetic energy. And so what we have done in this study is to understand whether the dynamo generated fields can support the jets that we see. So this is work done by, again, another PhD student, Santhia PS. I always call her my bravest student because she took up like an amazingly non-trivial task of working with these simulations and doing analysis of the data that is coming from these simulations. And so let me play the simulation for you. So you can see that there was a disk, and as because of MRI, magnetorotational instability, it becomes unstable in this turbulence, and then eventually there's formation of jets and so on. And so these are very beautiful simulations to look at. So what did we do with them? So the thing is that we have run 2D, basically she has run these 2D and 3D simulations. And the difference between the 2D and 3D simulation is that in the 2D simulation, we took these large colloidal ring initial condition, whereas the 3D simulation had like smaller colloidal rings. This was to enable, forgetting of the initial condition over a period of time so that the dynamo as a natural turbulent process can operate. And so you can see the difference in these two panels. So this is coming from the 2D and this is from the 3D simulation. And basically, what we see is that there is a remnants of the initial condition that's seen in the magnetic field. But in the 3D case, the dynamo is operating very robustly. And so you see these butterfly patterns, which is something also you come across in the context of sun. It's the exact same thing over here. Basically, the same guys acting. And so these are basically quasi-periodic oscillation of the magnetic fields and known as the dynamo cycles. And then these are jets. So this is from the 2D guy and this is from the 3D. You can see the 2D is more robust. That's also because the magnetic fields over there are retaining their initial memory, whereas here the magnetic fields are more random in nature. So the jets over there are slightly more weaker or less robust than the jets that you see in the 2D case. What is interesting that we see is that the pointing flux in this jet has a time correlation which maps to the dynamo cycle. And that is one of the most interesting results that we have got. The pointing flux is matching with the dynamo cycle. And the other interesting result is that actually the dynamo shuts down. Sorry, the jet shuts down. Dynamo continues, but the jet shuts down. And so what happened? So if you look at the Blandford-Znaik theory, then that actually takes into account the magnetic field on the horizon and the spin of the black hole and so on. There is this kappa factor, which is a fudge factor that has been proposed to account for the geometry of the magnetic field and is usually said to be order unity, but actually it is never really order unity. So this is something that we show in our work, that this kappa can be much smaller. And what we are seeing in our simulations is that in the 2D case, the kappa is such that, okay, we are basically plotting here some kind of randomness parameter. So if the parameter is equal to 1, the randomness is minimum. And if the parameter is less than 1, of course, the randomness increases and so on. So what we find is that in the 2D case, the randomness is around 1. But in the 3D case, it kind of plunges below a value of 0.6, and that's when the jet shuts down. And so this is another result that we see, and this we are going to submit soon. So the summary is that reconnection is important for magnetically dominated decaying turbulence in early universe and can explain observed fields in void. And dynamo and accretion disk can provide magnetic fields for jet formation, but randomness is going to be an important factor which will influence the black hole jet efficiency. All right, so now I come to this part where I want to just tell you about some of the common challenges I've encountered all through the journey. This is really like a laundry list of the things that I have felt. I don't have numbers. If you resonate with it, maybe some of you don't, some of you do, but I thought to kind of have this conversation, it is important for me to just flag everything that I felt like didn't work for me. So one of the things that I constantly feel is that there is a loneliness of being one of the few women in the institute or the department, not having enough people to talk freely without worrying. So I'm just going to read this stuff, right? Without worrying about gender dynamics. So it's easier to get isolated. Some sort of extra effort has to be made to communicate with men as opposed to women. Yeah, so again, it's harder to network and form collaborations because of all these gender perceptions and biases. You can be perceived to be problematic, or you can be perceived to be a distraction sometimes, or a crier. All of these things can happen. You can be excluded from important conversations. When it's important enough, then maybe you are excluded from the conversation, and you don't receive information about opportunities because your network is not strong enough as opposed to the other gender. So then the robust recognition is very slow process. On the other hand, if you are in meetings, there is some kind of hyper visibility because you're one of the very few women over there, and then it can lead to all kind of butterfly effects, like somebody is perceiving you to be like this or that, etc. And this hyper visibility can be also harmful. And of course, imposter syndrome is going to happen because you constantly not being acknowledged, or like you are not feeling like you're being included, or you're not feeling like you belong to the place, etc. And and when it happens that you're not appreciated enough for your work and your effort, then that can absolutely lead to burnout, and you have to watch for that one. That is a big one. Leads to anxiety issues. It's not being talked about enough. Mental health is a big. It's not just a women's problem. Again, it's a problem that almost everybody faces. Of course, you can get all sorts of negative attention, being singled out, or bullied, or being generally given a hard time. And of course, you can have unwanted overtures that makes it difficult to have conversations with people that you would actually like to have conversations with, because you respect their science. So this is all a set of stuff that I thought I'd share. And then there are, of course, challenges as faculty. This we've already discussed yesterday. I think once you stop collaborating with big names, the citations will drop. And this is not necessarily the case when you're part of big collaborations. So theorists have this problem more, right? I feel, because the only other person who raised this was Pallavi. And so, yeah, so this bothers me quite a lot. I cannot tell you how much this bothers me. And then, of course, the other things, you kind of token gender representation on committees and panels, which bothers me less. I mean, there are days when I can just say no because ICTS is ICTS, so it's fine. But sometimes you're just annoyed that you're just being asked to do things. Then, of course, it can happen that students do not accept your authority easily and can feel unduly victimized when you provide some kind of feedback, because, I mean, you're not even trying to do anything, but then you're perceived that you are doing something. So that is a hard one always. Yeah, but in this whole journey, The high was when I was offered the faculty position after all of that, the PhD and postdoc and everything. When the faculty position came along, I was very happy. Of course, I was also nervous about the next journey that was ahead of me. But what really empowered me was, formation of this group. And so there are days when I don't like my students, but most days I am very grateful that they are there. They are a lovely bunch of students. Yeah, so this is a platform to do long-term community things, I think, like forming groups and support systems. So one of the very first things that I did was to do this, women in astrophysical fluids and plasmas. I got a lot of international women researchers on the same dais forum, and that was really nice for 2 years because COVID had made it possible to have online things, and so it was really successful for a couple of years. But I got busy, and so like this is not so active anymore. But I would like to pick it up again at some other point. And of course, I think I always try that I create an atmosphere that encourages for more selection of more women and women students and postdocs whenever the opportunity arises. So with that, yeah, this was when the group was largest. Some of them have now left, postdocs who are now gone to other different places. Yeah, with this, I end my talk.
So yeah, very nice talk. Thanks. So I was wondering about, curious about the science part, where you mentioned about a role of spin of your black hole in terms of production of jets. So your simulations do take care of those black hole spins also when they are incorporating. And yeah, so and also the second part of the question would be related to the randomness on the fields. So how they are actually contributing to the quenching or existence of jets.
Sorry, come again with the second.
The randomness factor which you plotted. So
Yeah.
how is it contributing to the production of jets and how does it matter?
Right. So, okay, maybe I just go back to that slide. Yeah. Okay, the first thing that you said was about the spin, right? I mean, actually, the GRMHD simulations brought in the revolution because, because you could do the spinning black hole, and that could lead to these jets and so on. And then, like a lot of them basically did this whole exercise of, varying the spin as a parameter and how the jet power and the efficiency goes up and down according to the spin. And so spin is there in these. So this particular simulation and all other simulations have the spin included. So here in this case, it is some 0.9375. There we have done another simulation which is at 0.5 and so on. Now, coming to the randomness parameter, right? So most simulations, whether they are MAD or sane simulations, if you're familiar with the terminology, then basically they start with magnetic fields, which are like these nice laminar fields. Yeah, so they are also very large scale and so on. And so eventually you kind of the accretion brings in these fields. And so when you look at how the how the magnetic field on the horizon is, or how it looks like, it basically is going to be more laminar than turbulent. And what I'm trying to say is that in our other case, where we starting with a different initial condition that makes it easy to lose memory of it, then we do get more random fields which are accreted towards the black hole. And that's so if you go around the azimuth, then you imagine that the fields which are supposed to be these dipolar fields, right, they don't necessarily align with each other. They are changing sign and so on. So that is the reason, that is the randomness that I'm talking about.
So the simulations are matching up with the observations?
Yeah, so there have been these EHT observations, right? And so the claim is that, for example, the M87 one is a good match with the MAD model for the accretion flow and so on. And there has been an extensive, I mean, the GRMHT simulations have done an extensive study with the spin and so on, but of course the spin itself is not an easy observable. So
and also now with the randomness, I think this polarization measurements would also be some important insights about how the change in the configuration of your magnetic field structures takes place, and whether that is matching up with the simulations would be something insightful.
Yeah, it would be nice if there are observables.
I'm not sure about what kind of objects you are probing in or sources, because now there are observations of AGNs as well in X-rays, at least with the upcoming, X-ray polarization missions, of course, in the soft X-ray band.
Yeah. So there is this existing like anomalous thing that, in Sagittarius A, the polarization is basically lower than what you expect. And that's probably because of some turbulence.
Sure. Thanks.
You want to go ahead? Okay. Yeah, Pallavi, very beautiful movies. And so I actually have two questions based on two parts. The first one is, you said this A square integrated is a quantity you are using for those voids, right? But why not the A dot B? I mean, how do you decide which is?
Okay, yeah, good
both
question.
are conserved, right?
Yeah, well, you can have a system. So it depends on your initial system. So the system that we were looking at is basically non-helical. So I was looking at non-helical MHD turbulence. In the helical case, the answer is very easy. It is the helicity, as you have pointed out.
Because it is non-helical, you are using A square.
Yeah.
And related to this jet, So for 2D, I suppose you were adding some alpha effect to get the dynamo. I mean,
for the 2D,
did you have any alpha?
2D, there is really no dynamo as such. That 2D anti-dynamo theorems, of course. So there is no really dynamo. This basically is, it's just shearing of the poloidal fields. This one. Okay, but eventually it will get turbulent, and then the anti-dynamo theorems will tell you that this will not get sustained.
So you did not add any artificial, not artificial, any alpha effect?
No alpha effect. So this comes out, of course, with the disk will have stratification and so on, the density stratification. So maybe that, of course, it's MRI driven. So MRI is a different kind of a beast compared to, like the standard classical dynamos where you have.
Because I remembered Axel has a paper like 2D with an alpha effect. I mean, he's not using general relativistic thing actually, but there's an alpha effect. So I just asked.
Right.
So in this simulation, am I right in understanding that the disk puffs up as when you get it going?
Yeah.
So whatever you started with, the cone angle reduces significantly.
Yeah, I mean, the cone angle remains more or less whatever it is after a certain period of time. Initially, it is kind of thinner, but eventually it gets that whatever quadratic, the parabolic profile, and it remains so. But you're right that the disk itself becomes turbulent, so there is some kind of puffing up and so on.
So it is occupying that full volume.
This is like actually a zoomed in version. So if I zoom out, you will see that there is a cutoff of the disk.
Oh, I see.
So,
Okay.
yeah.
So what is the cell size here? How does a cell size compare with the pixel size or the resolution in the HDMI?
Yeah, this is a good question, and I don't. I don't have answer on the top of my head. I'll get back to you.
Yeah. Okay. So the field pattern that is seen there, is that consistent with what you find, or now we have there are data which show changing field pattern also. They have 3 epochs, and they have found that the field pattern changes between these epochs. So I was wondering how that compares with your simulation.
This changing of field pattern, is this the kind of Q transition, the Q cycle that you're talking about? No.
No, this is just observations between 2017. Well, no, when did they make the first polarization? Preeti, you remember? The polarimetry first, I don't remember, but there are 3 epochs for which they published the magnetic field. The same one, 2017.
You're talking about the EHT. Okay,
Yeah, the EHT of Messier 87.
Right.
The original data were from 2017. She says the polarization is also from there, but there have been 2 subsequent epochs after that.
Yeah, I haven't looked at the subsequent epochs, but actually those fields are they are not turbulent to begin with. Yeah, they're not turbulent, so I don't think they're resolving sufficiently. This is my take on it, but yeah.